Sure, it's used the gas law. So this means you have to write your gas constant into your information sheet, okay? Alright, basic measurement. We can have many ways of doing the measurement. Different way of measuring it has different degree of uncertainty associated with it. So we can do differential pressure drop method. Differential pressure drop means there's a pressure drop. Based on that pressure drop, we convert that pressure drop to the flow rate. Okay? So the meter is not actually measure the flow rate. The meter actually measures the pressure drop. Okay? It measures the pressure drop first. Then we convert that pressure drop to flow rate. What does it mean to me then? So if I have orifice meter has a hole. Okay? If the hole is too small, I have a lot of pressure drop. It is a restriction in the pipe. Okay? We should not have that. If the hole is too big, what happened to me? I don't have enough pressure drop to do any measurement. Okay? So what is the accuracy limit in the pressure drop measurement? What do you think? 1 psi, is that the accuracy limit? 10 psi. The meter that I have in the lab, the accuracy measurement limit will be about like 1 inch of water. Okay. If I get something about 1 inch of water, that is equal to not quite measurable. 0.1 inch of water is for sure cannot measure. Okay. 0.1 inch of water is very difficult to measure. 1 inch, maybe 0.5, we have more uncertainty. So this means if we have an orifice plate and we have the orifice hole that is too big and the pressure drop is too small, we will have a lot of uncertainty because they convert from pressure drop to flow rate, right? Okay. Venturi meter, how does a Venturi meter look like? Have you seen it? Who have never seen Venturi meter? Or who have seen it? Who have seen it? I have seen it several times because it is in the video. Elbow meter, flow nozzle, it is in the video. Rotary meter, rotameter look like this. It have a ball or some kind of restriction and we flow it up. Okay, then we read what is the measurement. Okay, this kind of measurement is very good, very easy to use, but it's not accurate. Uncertainty of 10% is like normal, okay, and it's not for high pressure application for sure. If you have too much pressure, it's gonna break. So that's a link for the video. Coriolis flow meter. I don't want to show too much video because it's boring. At least for you, right? You can. Are you going to promise me that you will not like sleepy or not talking too much when you show the video? Coriolis flow meter. I will show just the important part and tell you what to get. Okay. Coriolis flow meter measure the mass directly. Remember this. Coriolis flow meter measure the mass directly. Vortex flow meter is based on the vortex that it generates. What is vortex? When we have the restriction, we have the flow over the restriction, it has turbulent flow. At the end of this rough body, it creates a vortex. It's like a rotation that we can actually see. Okay. We have electromagnetic meter. Okay. It's used some other concept. Let's see just the one that important, okay?
Have you ever looked operates on this principle?
Oh, okay, I want you to see this.
The water is forced through the swinging hose. The hose twists as a result of the change.
You see, with and without flow. Okay, this is a water hose with and without flow. When there's no flow, we swing it, it doesn't twist. See, it's kind of straight. But when there's a water inside, it twists like this. Okay, So the degree that it twists depends on the flow rate. In the flow meter,
Angular velocity in the curved hose. That's the Coriolis effect in action. A rotabus operates on this principle to deliver the most accurate measuring results. See for yourself. For practical exploitation of this principle, it is sufficient for the two measuring tubes to perform oscillations on a small section of the circular path.
so the tube is vibrating already. Without any fluid movement, it doesn't twist. Okay? But if there's a fluid movement, it will twist.
This is achieved by exciting the measuring tubes with an electromagnetic exciter in its first resonance frequency. When no mass is flowing, the two tubes oscillate symmetrically. But when a mass flows through the tubes deform proportionally to the mass flow rate. This deformation is registered by two sensors and forms the basis of the measuring result. A phase shift occurs between the first and the second sensor. The mass flow rate is derived from this phase difference. Should further the density of the media need to be determined, it is simply computed by evaluation of the oscillation frequency of the measuring tubes.
So frequency tell me what? Density. The shift in the phase tell me the mass flow rate. Okay? That's it. So there's a pipe that keeps twisting. The rest, watch it for yourself, okay? And let me show you the one that is in the exam. How about that? Okay. The one that is important enough to be in the exam, which is Coriolis flow, and this
The most diverse substances are transported and distributed in piping systems every single day. They can include solvents and chemicals, oil and gas, or steam for energy transmission. The fluids flowing through pipes often have completely different properties. Therefore, different principles for their measurement are required. One method is flow measurement, based on the differential pressure principle. Some 300 years ago, Swiss mathematician and physicist Daniel Bernoulli discovered the direct relationship between the pressure and speed of a fluid flowing in a pipe. Italian physicist Giovanni Battista Venturi also performed experiments on flow, and in 1797, he built the first flow meter for closed pipes, known as the Venturi Tube. Here is how this measurement method works. Differential pressure flow meters have an artificial restriction integrated into the measuring tube, illustrated here by the example of an orifice plate. Two holes are located in the pipe wall, one before and one after the orifice plate. Two separate tubes connect these holes to a differential pressure sensor with its two pressure chambers, separated by a diaphragm. The tiniest pressure differences in the flowing fluid can be precisely measured. If the fluid is not flowing, the pressure before and after the orifice plate is essentially identical. As soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chambers of the sensor, a higher pressure before and a lower pressure after the orifice plate. This pressure difference is a direct measure for the flow velocity, and thus the mass and volume flow in the pipe. The higher the flow velocity and the resulting drop in pressure around the orifice plate, the greater the differential pressure measured. In numerous industrial applications, the orifice plate covers many needs of flow measurement technology. However, other designs are available for certain measuring tasks to minimize undesired effects, such as excessive pressure loss or abrasion of components due to solids carried in the fluid. This demonstration shows that an abrupt restriction generates severe turbulence in a fluid. Nozzles with a rounded, funnel-like inlet clearly reduce turbulence and thus create less pressure loss. Nozzles are particularly suitable to higher flow velocities or to fluids with abrasive solid particles. Turbulence reduction is even greater with Venturi nozzles. And finally with Venturi tubes, where the restriction is created by longer conical constrictions in the pipe wall. All these designs can be supplied with different restriction diameter sizes so that the pressure loss and the differential pressure generated can be optimized for the process conditions. Industrial flow measurement using differential pressure has been tried and tested in numerous applications worldwide for about 100 years. With this measuring principle, all liquids, gases, or steam can be measured, even at extremely high process.
All right, you get it, right? How does it look like for Venturi tube? It's a little bit longer. For the nozzle, is orifice plate plus a little bit nozzle extended. Okay. So, all right. In what year that Venturi, which physicist? Italian physicist invent the Venturi tube? 17. That kind of question is not going to be an exam, okay? And the point is, you know which one is for abrasive fluid. If we have solid particle, we don't want erosion. Is it preferred to use nozzle or just orifice plate? Nozzle, right? So whenever there's an abrasive or solid suspended in liquid phase and it flows a lot, so we don't want erosion, we can use Venturi or nozzle instead of just orifice plate. Okay? We need to have high enough pressure drop to do the measurement. So the rest is just other technique. Okay? When we have the measurement, most of the time, as rule of the thumb, the most accurate measurement is from which one? What kind of meter is very accurate? The one that is the most expensive, isn't it? The one that is most expensive most of the time is the one that is most accurate. So which one is most expensive? Coriolis flow meter, okay? Coriolis flow meter will give me very accurate, okay? But it's not the case if there is gas inside. So what we need to know is not just like, most of the time if it's not that much of a problem, we just use orifice plate for gas, okay? And if we want more accurate, we can use Coriolis. Coriolis can be, how big is a Coriolis flow meter? How big? It's like 2 feet, 3 feet? Really? Can it be like 6 feet tall? Yes? It can be very big, depending on how much is the flow rate, okay? And the last video, vortex measurement, you may watch it by yourself. I will try to assign that in the homework, okay? But the one that we should watch it together is this one. Impact of two-phase flow.
Hi, my name is Joel Weinstein with Micromotion. Today I will discuss how entrained gas can affect the Coriolis mass flow meter. There are two main things to consider when working on an entrained gas application with a Coriolis meter. First, what does the meter actually measure? Second, what are the sources of errors? As with all meters, Coriolis meters are only capable of measuring what goes through them. If the process fluid is a mixture of liquid and gas, then we accurately measure all mixture properties. We measure mixture mass flow, mixture density, and mixture volume flow all properly. In applications involving liquid flows with small amounts of entrained gas, mass flow meters have an inherent advantage. Users typically want to know the liquid quantities, not the mixture quantities. In the case of mass flow measurement, the mixture mass flow, which we measure, is nearly identical to the liquid mass flow because the mass of the gas is negligible. The same is not true for density and volume flow. For example, if 2 barrels of oil and 1 barrel of air flow through a volumetric flow meter, the meter will simply measure 3 barrels, and thus will over-report the amount of oil. Now let's discuss the errors associated with entrained gas. The primary source of error from entrained gas in Coriolis mass flow meters is called decoupling. There are other sources of error such as compressibility, but decoupling is dominant. Decoupling happens when the fluid inside the tube doesn't move exactly with the flow tube. When that happens, errors occur, which are dependent on meter and fluid properties. In the case of single-phase flow, there is only liquid inside the tube, and the center of gravity, the green square, moves directly with the center of the fluid. So all is well, and there is no error associated with decoupling. However, in the case of two-phase flow, the bubble can move separately from the liquid, which ultimately causes the center of gravity to move separately from the flow tube center of gravity. And in the case of high viscosity, because the viscosity grabs onto the bubble, there's very little motion of the actual bubble, and therefore very little motion of the center of gravity. So we have very small errors. In the case, however, of two-phase flow with low viscosity, it turns out that the bubble can move further on each oscillation than it could when there was higher viscosity. And what this causes is even greater error inside the tubes because the fluid is moving separately from the tubes. In the case of high frequency, low viscosity, we basically have a worst case scenario. In this case, decoupling is the greatest, and the bubble moves further than it could in any other scenario. Therefore, the errors are the greatest. While Micromotion manufactures meters with a range of frequencies from low to high, our low-frequency elite meters are recommended for applications involving entrained gas, as they are usable over a much larger range of gas volume fractions.
So the low frequency Coriolis flow meter will be more expensive. And if we have a lot of flow rate, the bigger it is like even more expensive, okay? Maybe this one is okay, 16, 30, 60,000 or something. Or maybe 100K, depending on how much is the flow rate. It's very accurate, and we need it very accurate because we don't want any error. Small error means a lot. 1% could be $1 million, okay? So that's why we need it to be very accurate. All right? When we have gas, Coriolis flow meter measure very accurate. But if we have too much gas, like he said there's a separation of the center of gravity and the center of gravity of the fluid and the pipe. So when that not in the same location, the calculation that show the answer will be somewhat wrong. Okay? So you can compensate for that by buying a low frequency or buy a bigger unit. So if we buy a bigger unit, what happens? Okay, we have bigger unit. The pipe is huge and it's vibrate. So when the pipe is huge, the velocity that goes through is not that much. Okay? When we don't have much velocity, then I think there will be less error. The range of which one to buy, you can look in their website. Depending on what kind of flow rate, then you look, okay, this flow rate, use this flow meter, we have that much error or something. It is already tested and documented. Any question? Okay, where do we use Coriolis flow meter? In the tank battery, if we are going to use Coriolis flow meter, where is that going to be? On the lag unit. You have seen it, right? Okay. Alright, video. You'll be assigned to watch some of them. Okay.
So now out of the OTC though, there's a Coriolis meter that's just in some
Hidden
stuff.
in the high pressure thing in the back,
So
right?
that's not in a LAC unit though.
That is not in the lag unit, that is a measuring section. Okay. That is, I don't think that's for onshore either. I have to check with Danny, but on the lag unit, it's either Coriolis flow meter or A.O. Smith. Okay. Alright, how do we select the meter? Okay. To select the meter, we have to know how much accuracy we need. Okay. Expected useful life. Okay. Range of flow rate, temperature, and do we need power to operate it? Is it for gas or liquid, or is it for both? How much does it cost? And availability. And the last one, susceptibility or to theft or vandalism. We may not put a very expensive flow meter if it is going to be stolen. Okay. In most of the equipment or the apparatus, the facility, the flow loop, okay, one of the expensive part is the flow meter. Alright, this is a positive displacement type. Okay, we don't actually pump it, but we measure it. We take a certain volume in and let it out. Take a certain volume in and let it out, and then we count how many times that we do that. Where do we do this? Okay, look at A.O. Smith meter. This is on the lag unit. Okay, it's a positive displacement type. It works like a vein pump, okay, except it doesn't pump. Okay, it looks like a vein pump, but it doesn't pump. It takes a certain volume in and count and let it go out. Okay, and it registers every time that it moves. Then we know how much coming out. Okay, this is PD type flow meter. Diaphragm type gas meter is a residential type that we use in the house so that we pay the gas bill. It takes a certain volume in and push a certain volume out. It's a positive displacement type of the flow meter. Okay. Positive displacement means we directly measure the volume that we push or we move forward. Okay, this is a positive displacement type. The differential pressure type means we create pressure drop, then we measure the pressure drop. Right? They are not the same. Volumetric measurement. Okay, this is some calculation. Basically, they use a gas law, and they find out the difference in the register. So we have flow rate equal to volume, okay, pressure and temperature. Where does this equation come from? Is that PV equal to ZnRT or something? Okay, simplest method, measure gas by volume, then it displace, then it count how many pass by. Okay, this is for residential type. I don't have the example of this, but that's the equation that they use. And okay, this is a derivation. Okay, PV equal to ZnRT, base pressure, base volume equal to base pressure multiplied by flow rate multiplied by N, R, and T. Okay, this is base pressure. Volume that they report will be volume at the base pressure. Right? Then combine those two equations, this equation divided by that equation, then they get that. Rearrange it, get that. Okay. Q is a base volume at a certain pressure. V and T is a volume and pressure of measurement. What does it mean to me in this case? Is it accurate Is it accurate enough to do it like this? Whenever we do this, the assumption associated with it is Z is 1. Okay, Z is 1. So this means if I have the flow rate, I need to know temperature. Okay, I need to know temperature. I need to know pressure inside. If I don't have accurate temperature measurement and I don't have accurate pressure measurement, my reading will be wrong or a little off. Okay. Sometimes we don't need that much accuracy for the case of like residential case. So flow meter. So this thing implies that we don't just need pressure drop. Okay. This is a meter run, right? What else do we need? We need Z factor, most likely. Actual pressure and the temperature associated with it. Let's take a look on how they change it. The orifice plate look like that. Okay, that is the orifice plate. There are senior fitting, Daniel senior orifice fitting, and the junior fitting. Senior fitting means we can take it out at the same time that we keep it flowing. Okay, so that is senior orifice fitting. What they do is they kind of isolate it. After we isolate the flow part, then we can take this thing out. There's a video to watch, but we just don't need to know that. This is just a concept. Okay. When we take the orifice plate out, okay, what if we flip the side and put it back in? Is that okay? Is that okay, Katie? No. That is going to create a lot of error and no one knows. Okay? That is number one source of uncertainty. They take it out, inspect it, flip it, put it back. Okay? That is bad. So this leads to this picture. Look at this picture carefully. The part that is very important to note is one side, you see this blade, it looks like this. Okay? It looks like that. So one side is sharp edge. Another side is not that sharp. The sharp edge faces upstream. If we flip it and the sharp edge faces downstream, that's gonna cause error in the measurement. Okay? So that's most of the time that is in the exam. The sharp edge need to face upstream. What else is in the exam? That name, Brenner contractor, smallest diameter of the flow stream. So when we have the flow converge, okay, and go through, and look at the smallest diameter of the flow stream. The point in this picture is the point that is smallest in the flow stream is not at the orifice plate. It's a little bit behind the orifice plate. Okay, it's not at that point, so it converges even more afterward. And that point they call Venner contractor. Okay, classic final exam question. We have the orifice plate. I give you the P1, P2, P3. Maybe I delete all this. Which point has what pressure? Okay, upstream. So orifice plate work by we create pressure drop. Then we measure the pressure drop. Convert that into flow rate, right? So, which point has highest pressure? Of course, upstream has highest pressure. Okay, it's highest pressure. Downstream, far away from this, have low pressure. But between, okay, this part that we have circulation, is have even lower pressure. Okay? The lowest pressure in this picture is not P3, but it is P2, okay, where we have Venner contractor. Okay, so why is that? Who want to help me? Next to, oh yes,
Higher velocity.
higher velocity. Okay, when we have Venner contractor, the cross-section area of the flow stream is smallest. This means at that point, the middle point flow fastest. When we flow fast, according to Bernoulli law, we have lower pressure. So that is why this is lower pressure. Okay?
Does that point, the
Venturi contractor.
change with your flow velocity or your flow rate?
Most of the time, this thing, when we put this over there, the downstream is disconnected from the upstream. So it doesn't really depend much on the upstream. But if it flows real slow, yes, it changes.
Okay.
But in a certain range, it won't change. So this means this flow meter is accurate for a certain range, not from 0 to something, but it will be a certain range. Maybe like 10 to 90% of the reading scale, that is okay. If it go close to 0, this means there could be the change of that location and it may have more error. Okay. Orifice plate is commonly made of sharp edge, circular orifice. Any rounding of the sharp edge results in error in measurement. Okay. Venturi contractor is about 0.35 to 0.85 diameter downstream. So it's not at that point. Alright. This thing we have, where do we have pressure measurement? Where do we read the measure pressure? From this hole, right? From those holes we can get the pressure measurement. One more thing to note is, where do we install the orifice plate? So when I have a meter run, it's go up, and its pipe is very long, and it's go down. So the flow is come from this side and go down. Should the orifice plate be located at location A, B, or C? Maybe B, right? Okay, C maybe is a little bit difficult to like. Most of the time, whatever happens downstream should not do anything with upstream, but it can. Okay, there could be two-way communication. So most of the time that we worry about is enough length for the flow to be fully developed. So the location should be far away enough from the entrance. Okay, if we cannot do that, we may put this thing in. Okay, we can. What do we call this? Okay. Dampening device. Okay. So this is to straighten the flow line, the stream line. If we don't have enough distance from the inlet before the measurement point, we may put this dampening device.
Is that a dampening device or a flow conditioner?
Flow conditioner, I'm sorry, flow conditioner. This is flow conditioner. Dampening device is something else. Alright, we have two way of measuring the pressure. One way is have the hole on the flange itself. We call that flange tap. Okay, flange tap. Another way is get the hole on the pipe and we do the measurement. We call that pipe tap. Okay. So this is for flange tap and pipe tap. Which way should we use? Which way should we use? Who wants to help me? It doesn't matter actually. Because each way we have the table for itself. But if we use one way, we have to use the right table to do the reading. That's what it is. Okay, don't mix them. Pressure tap. Pipe tap, maybe we use flange. Pipe it's okay. It can be still okay, but it causes more error. So we have secondary component, differential gauge, static pressure gauge. What is that for? Pressure gauge. Measure the pressure, right? If the pressure gauge go wrong, everything is wrong. Okay. So we recommend use the flange taps, not the pipe tap, but if we need to, we may use the pipe tap. What's wrong with using the pipe tap? Why do we have more error? What do you think? Pipe roughness. Look at this pipe. So pressure drop on the flange cap will get the pressure across this thing, right? But for the pipe tabs, it has to take into account of the pressure drop due to flow in the pipe over here, and that pressure drop is dependent upon pipe roughness. When we buy it new, it may be very smooth. Over time, it's more rough. Okay. Here's the equation associated with it. Okay. There's a derivation, and more derivation, and at the end you get this. Okay. The final form is Q equal to C prime square root of HW and P sub F. HW is differential pressure in inch of water at 60 Fahrenheit. Pressure is absolute static pressure, PSIA. Okay. Where else do we use PSIA? I see in the exam some of you use PSIE instead of PSIA for the compression ratio calculation. That is straight to zero. You know that, right? So when you pressure compression calculation, use PSIA. Okay, C prime multiplied by that square root. C prime is from the table. Okay. Next class, we are going to talk about what is that, where does that come from, like those things that we skip. Okay. But that is the end. One thing before you go, what you need to know is what is the biggest factor in C prime. Okay. C prime is a combination of several terms, F sub B, Y, blah, 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 blah. Which one is the highest value? Okay. Or which one change most? Let's take a look at basic orifice factor. Basic orifice factor is depend on the location of the tap, the internal diameter of the run, the size of the orifice. Okay, so it's depend on the size, internal diameter. This thing is the most important, F sub B, because it changes a lot. It can go from 12 to 1,000, depending on the size. Okay. The rest, you see this thing, okay, 0.008, 0.006, that's F sub R, doesn't change much. Something else may be 1, okay, sometimes it's 1, sometimes it's 0.98 something, so it's not that big of a deal, right, between 0.98 and 1, yes, it changed, but it's not that much. Y1, look at this one, 1, and this is 0.9918. It doesn't change much. This is other parameter. 0.998 something, 1.00 something. So which one is most important that we need to make sure that it's really correct, or the one that contributes most? F sub B, basic orifice factor, this thing, okay? Memorize that. Other factors, so basic orifice factor is dependent upon the size of the orifice. So this is dependent on the flange tap or pipe tap. Okay, I didn't show that table. So this is for flange tap, and we need to know orifice diameter, pipe size. How big is the pipe? How big is the orifice diameter? So this dictates F sub B. Okay, very important, the most important one. There are several other factors that contribute into this constant calculation. The rest is to account for some minor things, like the change in elevation, change in the Reynolds number or something. We will cover that next. Okay, it is almost the time. Let's move forward to, is it the time? One reason that make the error is pumper change the orifice plate and that's not noted on the chart. Okay, that's number one reason. The error. Okay, see you next time. Oh, it's just 12:19 with my cell phone, but okay, I let you go. We do not have TA office out this afternoon. If you have questions about the homework, which is very easy, please come to see me. Okay? The partial project due Tuesday. We will scan your exam